who's a Vanney Fellow at Leiden University, who's going to talk to us about radio stars and exoplanets.
Thanks, Sandra.
I assume I'll give you a 3-minute warning.
Yeah, sure. I assume you can see my slides all fine.
Yes.
Yeah, great, thanks. Yeah, so thanks everyone for attending my talk, and thank you to the organizers for giving me the opportunity. I feel a little bit of an outsider here. I'm going to be talking about radio stars and exoplanets, and hopefully towards the end of my talk, I'll see how all this kind of links in with the themes of this conference. And yeah, so just thanks for letting little outsider give a talk here. Before I get underway, obviously all good science really isn't done in isolation. It's done as part of a team. And particularly here, I just want to acknowledge Harish Vedantam, Tim Shimwell, both based at Astron, Ben Pope at NYU, who's now just started a tenure track position at UQ in Australia, University of Queensland, and Alina based at Trinity. Without their smarts, I wouldn't have been able to present half these results as I'm about to go through. So I probably don't need to tell people on this call that there's a current population explosion undergoing in exoplanets. It's this kind of amazing time to be alive when, I wouldn't say it's easy, but it's become standard now to find a planet around another star. And so that's quite a phenomenal time to be an astronomer, but there's some big unknowns here. And there's a big unknowns that I'll touch on, but in particular, we know also because of missions like TESS, this revolution is now occurring around the most common stars of our Milky Way, in particular, M dwarfs. These for people not familiar, about 10% the size of 10% the mass of our sun, a little over 10 times Jupiter. And this has some really interesting implications potentially for habitability, because if you're familiar with the TRAPPIST system or any other M dwarf systems, the idea of the conventional habitable zone, in quotation marks, conventional is the key word here, this is shrunk. So if you want to have liquid surface on the liquid water on your surface of your planet, you have to be orbiting closer than the orbit of Mercury around these M dwarfs. And so this has very important implications for understanding potential habitability of these planets, because we know sometimes the star is not a great host. For example, with our sun, we know it undergoes these massive eruptions called coronal mass ejections that spew plasma into the interstellar medium. And we know these CMEs are the greatest impact on space weather in the Earth-Sun system. So that's really important to understand. You can imagine if you shrunk this orbit to be so close to the star, the chance incident of an impact is significantly higher in the face of this activity. And the other one big unknown that we really don't have on planets outside our solar system is, what are the magnetic field properties of such of these planets? What I'm showing you here is a simulation of the Carrington event. So this kind of dense CME that hit and hot CME that hit the Earth in the 1850s. And what you're seeing here in the magnetic field is just the impact of this, and the magnetic field is traced by these white lines. It's just a simulation, but I'm just trying to point out that we think that the Earth's magnetic field is a very important property for essentially maintaining the atmosphere in the face of such activities. So I'm a radio astronomer, so I'm probably going to say the answer here is obviously in the radio. So one big important tracer in the sun system of being able to identify CMEs are what are called type 2 bursts. So on the right here, what I'm showing you is just a dynamic spectrum. So it's frequency on the y-axis, time on the x-axis, and you can kind of see this characteristic sweep, this beautiful structure. This allows you to trace essentially the electron content and the plasma density of the material ejected from the sun, and you can just essentially directly trace back the density. So low frequency radio emission is one of the few only unambiguous traces of such CMEs. And the other one, which is a really nice experiment here, is that we can actually get a direct probe of the magnetic field of the exoplanet using particularly low frequency radio astronomy. And this is modeled off the Jupiter Io system. So for people not familiar, Io is a conductor and Jupiter's rotating quite fast. Its magnetic field sweeps over Io, and it's essentially just an electrodynamic engine, just like what you learned in high school. You've got a conductor and a changing magnetic field, and you set up a current which drive these beautiful aurorae on the surface of Jupiter. So my colleagues and I just had this idea of the unfortunate part of this. Even if we put Jupiter at some sensible distance, say 10 parsecs, we'd never be able to see it even with the most sensitive instruments that we have operating at low frequencies. So what we need to do is kind of boost the luminosity from the system to be able to try and do this science. And it was a reasonably simple idea, and people have thought about this for a while, But the idea here is now, well, one way we can boost the radio emission from here is if we replace, say, Jupiter with a star and Io with an exoplanet. And that's one way to drive the radio emission to be bright enough for the current generation of low frequency instruments to be sensitive to this emission. So that was a pretty simple idea. We went out and pursued this with the radio telescope called LOFAR. It's situated mainly in the Netherlands, but has stations spread out throughout Europe. And what you're kind of seeing here are these black tarpaulins are more or less just fancy coat hangers. And we just got so many of these on the ground that this science is now feasible when it wasn't 10, 15 years ago. And so in particular, what's unique about this instrument, say different to people familiar with the VLA or the compact array, it's sensitive to frequencies between 10 to 150 megahertz. And that's where you expect this emission to be, because it cuts off at higher frequencies, as I'll explain in a little bit. So at the start in 2019, and we published in 2020, we got our first detection of M dwarf. I'm just showing you it here to give you some background. The details aren't too important. We just have two epochs, one on the left in June, one on the right in May, about 2 weeks apart. And what you can see here is a source turn on and disappear in the other epoch. And there's just background radio galaxies for reference in the field. And this inset here is showing circular polarization. So to give you some background, I haven't got a lot of time to go into all the details, but essentially it's greater than 80% circularly polarized, and the emission is minimally variable, and it's on for 8 hours. It doesn't look to be bursty as you would expect from observations conducted at gigahertz frequencies of M dwarfs. And what's peculiar about this star, it's probably the most boring star you can imagine. So a priori, when we set out on this science goal, we would have thought we would be seeing predominantly active stars, which we do, and I'll come to touch on that in a second. But this star, GJLM51, rotates at 130 days, plus or minus 30, because obviously constraining such long rotation is very tough. But also very X-ray quiet, and we've analyzed a whole bunch of optical monitoring data on this, and it hasn't really been seen to flare at all. So it's probably the most boring star you could pick. And so why are we getting such bright radio emission from this star? So in this paper, we go through, and because we know the emission's coherent for non-radio astronomers, because it's highly circularly polarized, you can be confident it's not synchrotron or gyrosynchrotron radiation. So you're left with either plasma emission or electron-cyclotron maser instability. I don't want to go into too much depth for this audience for the different plasma emission processes, but more or less because of the properties of the star, the fact it's so quiescent, we can begin to rule out different types of ways of driving this. And particularly the slow rotation is very important to be able to rule out, say, breakdown of co-rotation, because you remember that image I showed you of Jupiter where you got this beautiful ring of aurorae. And the reason that ring is driven is because Jupiter's rotating so quickly, around, I think it's 10 or 11 hours. While this star is rotating so slowly, so you can't drive the radio emission through that rapid rotation. And so what we've hypothesized in this system is the idea here is that you just deposit an exoplanet in the system within, say, a 1 to 5 day orbit. It can be anything from Mercury to Neptune mass, and you can drive the beautiful, you can drive this radio aurorae. And so this gives you a direct tracer, not actually of the magnetic field of the planet itself, but of the star. And so we know there's at least a 20 Gauss field sitting on this M dwarf. Where exactly it occurs, I'll come to touch on in a second, and why particularly CDI imaging of these stars is really important to help us, the radio astronomers, interpret this radio emission and probably extract the most amount of physics out of the system, as I'll touch on in a second. So that was just our first detection. We've been conducting an all-sky survey using LOFAR. It's a survey called LOTS. And we've covered about 20% of the northern sky, and we've just been trying to find stellar systems. And we've found pretty much what you expect. We've seen 8E Leo, we've seen some of the active stars, but we've also got a whole bunch of these quiescent stars. This is a little bit of an older slide. We've got about 6 what I call quiescent stars like GJ1151 that you just didn't expect to be radio bright before we started this survey. Now, and there's also a whole bunch of other stuff. If people are interested, feel free to come talk to me at the end. RSCVNs, BY DRA, really close, young, chromospherically active stars. A lot of interesting physics you can derive from those because the binary parameters are so well known. But let's just focus on the M dwarfs for this talk. So what stars do we see? Well, somewhat unique. What I'm just showing here is a Hertzsprung-Russell diagram, which is just on the top here. And this is just all stars within 50 parsecs from Gaia, DR2. And in the red, I'm just overplotting all our detections. What's reasonably unique here, as opposed to, say, observations that were done at gigahertz frequencies with, say, the VLA or the compact array, is that we're not biased to late type objects. It seems to be we're sensitive across the whole main dwarf, M dwarf main sequence. Quite different than what's been seen previously, where a lot of the detections tend to be M4 and later. And we don't see this. Obviously, these are low number stats, but there's the most number of stars we've ever had at low frequencies, about 20 odd. And of M dwarfs, and you can see that we don't seem to see any class more preferential than the other, and this is just shown in the detection percentage at the bottom with different bins. I didn't want to bore you too much with all the diagnostic plots, but I thought I'd just focus on one. This is kind of similar to, we saw yesterday, this kind of way to trace activity on these M dwarfs. For X-rays and H alpha, you often show this Rossby number versus X-ray luminosity normalized by bolometric or something similar. There's a similar-ish relationship in the radio that's been known for a while, which is just the luminosity in the radio, or the surface luminosity in the radio against Rossby number as well, with fast rotators down here on the left, slow rotators on the right. And this is just a gigahertz frequency, the archival information I'm showing here. And so the M dwarfs tend to be isolated that have ever been detected in the radio to Rossby numbers less than 0.1, and only really G dwarfs sit out these really high Rossby numbers. And you can see this kind of correlation. And this has been used as evidence for tracing dynamo activity and trying to understand the dynamo that's happening in these objects. Now, for our stars, we don't see that trend at all. And so just keep in mind that this M dwarfs tend to be 0.001 Rossby number than 0.1. This is our sample now in Rossby numbers, and we just pretty much trace everything that we just saw there. So don't worry about the symbols too much, but what I'm just trying to show here is that we don't see any kind of correlation in this same parameter space. And this, I think, says to me that we're seeing, probably different types of emission from these types of stars. Some of these are probably driven by plasma processes, but other of these, it would make sense if it could be driven by star exoplanet interactions, because then you wouldn't expect a correlation in this domain. But there's lots of caveats to that understanding. But really, to draw your attention, you can see we have M dwarfs. These aren't massive objects with Rossby numbers incredibly high, but we're seeing very bright radio emission from them. So maybe just to touch on the synergy of what that might be of more of an interest to this group here, I'm just going to focus on a target example called WX Humor. For people familiar, I'm sure lots of people on this phone call are with this star. Very active M dwarf in a wide binary. What was really useful here is that we had the ZDI maps from Marin's 2010 paper. And what I'm showing you here is just the dominant magnetic field properties in the object, in the star, with radial, azimuthal, and meridional modes of the object in 4 different years, or 4 different exposures. I think it's 3 to 4 years. And what you can see, it's predominantly a dipolar field. And having this information and actually having an idea of what the magnetic field surface properties were, we can really start to understand the radio emission from this object, because it looks reasonably weird. So this is the radio emission, the spectra of the source. I'm just showing how it's detected at our lower frequencies and pretty much disappears by the higher frequencies. And we have 3 different epochs: the red, the black, and the blue, and it seems consistent, reasonably consistent across the epochs, that we have this cutoff in the frequency space. And for people familiar with the radio emission, this it gives you a direct probe of the magnetic field strength if you've got electron cyclotron maser instability. But what's powerful here is, because we have the ZDI map, we can make some assumptions. Because WX Humor is so coronally active, we can't rule out plasma emission as easily, say, for GJ 1151. But what we can say is that we can say how far the closed field region extends because of this magnetic field. So what I'm showing on the right is frequency against radial distance in stellar radii for just slightly different base coronal densities, limited by the X-ray uncertainties on the system. And the yellow region I'm showing you here is essentially the constraint of our of our low-fire observations. As you saw, that we more or less cut off at around 140 megahertz. So this means that likely this radio emission that implies that our closed field region extends to at least 10 stellar radii, and that's about a factor of few larger than the solar value. And I think this means our results are showing that, and I think this is starting to fit consistently with the literature as well, and some of the results coming from the gigahertz higher frequencies, is that the magnetic field structure of some M dwarfs is in between the sun-like and planet-like configurations. So we have these compact, over-dense coronal loops with X-ray emitting plasma coexisting with large-scale magnetosphere with that is essentially plasma depleted and in a closed field magnetic geometry. Now that's I really hope there's some MHD experts out there to really understand how these systems can be set up. But like, yeah, there's these incredibly underdense regions next to very, very dense regions. And so the magnetic field parameters are very interesting in how you can set this up. But that's what we tend to be seeing in the radio. Just to finish, there's some unique stuff. Just what we'd really like help with in particular is that we're seeing these very highly confined bursts. So this is just an example of a highly circularly polarized burst from another active M dwarf binary called CR Draconis, CR Dra, which we just published earlier this year. And it's elliptically polarized. So we're very confident here. This is electron cyclotron maser instability. So you're talking about these plasma density cavities that are less than like 6 electrons per cubic meter. So incredibly underdense regions. And what's unique about this system is that pretty much we see it 100% of the time. So every single time we turn on our radio telescope and look at this source.
3 minutes.
Thanks. Yeah, I'm on the last couple slides. Thanks. We pretty much see it on 100% of the time. So whenever we point a radio telescope, for people familiar with electron cyclotron maser instability, this is beamed like a lighthouse, this emission. So like if you go to Jupiter and Io, you will see it turn on and off, kind of like a pulsar. It's a little bit more complicated because it's on the surface of a cone, but at the end of the day, it's an on-off process. And so how are we seeing it 100% of the time? This is telling us something about the magnetic topology of the emitting source. It's a little bit more complicated with CR Draconis because it's a binary or a triple system, but trying to understand this would be, getting CDI maps of this would be very, very useful, and some of our other detections. If people are interested in this, I'm more than happy to discuss offline. So just to conclude, and hopefully it's been a bit of a whirlwind tour. I'm sorry about that, and I'm sure I threw around a few terms that didn't make sense, but happy to take any questions about it. So just first detections of stellar systems at low radio frequencies. Our discoveries, what we're really doing is we're kind of probing 2 unique parameter spaces with these detections. One is the outer corona of these stars, quite extended, as you saw, up to 10 stellar radii for stars that we really know the magnetic field properties. And potentially we're seeing, as I showed for GJ1151, potentially seeing a different source of emission. And if we have the ZDI map of that parent star, then we can see how they correlate and where this emission is actually occurring in the magnetosphere of the star. Yeah, so that's where the ZDI maps of these stars are crucial for determining the emission mechanism and the exact coronal conditions. And if you're interested, there's a few papers there to check out, and I'm happy to take any questions. Thank you.
So thank you, Kirk, very much. Are there any questions? Moira.
Hi, Joe. Thanks for a really interesting talk. That was fascinating. I was wanting to ask you about the first star you mentioned, GJ1151, if that was right.
Yeah.
You said it was quite a slow rotator. I actually missed the rotation period as it went past. But I wanted to ask you how the rotation period is determined.
Yeah, so we have a collaboration with the MERTH team at Harvard. So it's photometric rotation period. So this is this is work done by Jen Winters and Dave Charbonneau and Jonathan Irwin at Harvard. And so this is right at the edge of their monitoring campaign, because they have about 360 days on this object. So it's 120 plus or minus 20 days. And that actually makes it hard for our follow-up, because knowing exactly the right rotational phase of the star to follow up with our radio observations would be really useful for star-planet interactions, because they should only occur at quadrature. But anyway, I think that's extra detail. Did that answer your question?
Yes, yes, I was thinking of how easy it would be to do ZDI on it, but there are better people to answer that question than me in the audience.
Yeah, no, I think that's the irony, right? Where this GJ1151, because it's rotating so slow and it's not active, we can be much more confident on the star-planet interaction, but then that makes ZDI mapping much harder. So it's like there's a catch-22 here. But as I said, WX Humor and stuff like that are fascinating, and there's these active stars. It's harder to rule out plasma emission in those environments, but is by no means conclusive. Electron cyclotron maser or a planet can equally drive this emission in these active stars as well. And we know active stars obviously have to have planets.
And Simon has, sorry, Moira, go ahead.
No, I was just thanking Joe.
Okay, Simon, you have a quick question for Joe.
Yep. Hi, Joe. Great talk. Thanks. I just wanted to ask a question. You had a slide where you had an image taken from Sebastian Pineda.
Yeah, you want me to get it up? Sure. It was the just artist impression.
I think so. Yeah. Yeah.
Yeah. Maybe let me just scoot out and then I'll share my screen again. Sorry, just give me a second. I assume it was this one. Sorry. Thought this would be quicker, but probably wasn't.
Yeah, that's the one. I was just wondering if you could say a little bit about what you think the implications are for the source of emission along that line. I know you said that the ZDI maps are necessary to find out where the emission is occurring in the system. But given the frequency of emission you're detecting, what the implications for that would be for the planet's magnetic field if the emission was coming from close to the planet?
Yeah, so that's an a really good question, Simon. So with this is essentially a subalfanic coupling, right? A subalfanic interaction. So the reality is Aurora is always being driven closer to the star than it is to the planet in this circumstance, right? The planet is kind of just the fuel, the thing that closes the circuit to drive this Aurora, and where the plasma torus and everything else produces, like in the Jupiter Io system's up for debate. And this is one of the arguments we have with some referees, and it's a fair argument. How do you maintain, say, a plasma torus in a star that has a corona? Again, I'll wave my hands and go MHD simulations and not know the answer. The idea here is backtracking to the magnetic field properties of the planet is quite model dependent, and you really got to understand the topology of the star. So we aren't confident to say exactly what it is. At the low frequencies, we know we're tracing emission. The magnetic field has to be greater than 20 Gauss, essentially, 30 Gauss. So that's hard. That's easy to get in the outer corona of M dwarfs. 20 Gauss field on a planet of Earth-like is probably unlikely. But I should say, and this is work we're doing, we're following up some of these systems with VLBI, so very long baseline interferometry, so we get milliarc second resolution. We can't do that at low frequencies, but we can do it at about 1.4 gigahertz. And with WX Humor, we're tracing it, and it seems offset from the Gaia position. And so that would imply then potentially emissions coming directly from the planet. If that's the case, then we can directly correlate the magnetic field properties directly to the planet itself, rather than doing a model-dependent backtrack. Here, if we have a ZDI map, we could do that. It'll probably end up with like a 20% or 30% error on the planet itself, but it's plausible. Maybe, does that answer your question? It was a bit of a rambling answer.
It does, yeah. I just wanted a little bit more information on that. That's great, thanks.
So the big win here in terms of trying to probe magnetic field strength is trying to just find free-floating planets or free-floating brown dwarfs, which we've also done. The idea here is that we just look for circularly polarized sources in the sky, and we just followed it up with say, doesn't have an optical counterpart, and then we just chased it up with like Gemini North and Keck, and we found a brand new brown dwarf. And so that then tells you you've got something planetary mass in quotation marks, like it's a T6 dwarf, so like we're talking 10 times the mass of Jupiter or a bit less. You're tracing 20 to 30 Gauss field. So like this 10 Jupiter mass object must possess a magnetic field of that property. But that's been known for a while as well from VLA work, right? Brown dwarfs weren't expected to have kilogauss fields, but here we are, they do. Yeah.
Okay, Joe, thank you.